Hello, my name is Sergey Zubkov, and I'm an allocator user. And so are many other programmers. Anyone who uses standard vector, standard string, any standard type that does what it does using allocators behind the scenes. Allocators have the well-earned fame of being difficult to write. I had to do that a couple of times myself, and I'm not going to tell you that it was easy. What I want to talk about is what that work achieves. So first, a brief refresher. What do allocators do? Despite the name, they do not just allocate. An allocator is a customization point that controls 5 different policies. It determines where uninitialized memory comes from, how uninitialized memory is disposed of, how objects are created in that memory, how objects are removed from that memory, and what it actually means to point to an object in that memory. We'll show a couple of examples of how that works. And of course, we now have 2 complementary ways to use an allocator in C++. We can provide an allocator as a template parameter, just like any other static policy. And or we can use the C++ 17 approach and provide the allocator as a constructor argument to one of the containers from the PMR namespace, in which case all the containers have the same type, even though they're using different allocators. There are benefits and drawbacks from either of those approaches, and as always, it's an engineering decision how to use each one, and going through implementation details of that would take forever, and we have plenty of talks at this very conference on doing just that. In fact, the talk by Alistair Meredith that just ended in Barry Hall was talking about the details of PMR. So enough with the refresher for now. Let's talk about what we can do with allocators. This is a short talk, so all I'm going to do is look at a few of the allocators available in the wild. In particular, we'll try to cover each of the ways allocators are used and show a few examples of all of these approaches. The simplest allocator that I have encountered that's not simply instrumentation, not simply an instrumenting allocator used for testing or tracing, was something called secure allocator, reinvented over and over in different libraries. So what it does is it attempts to make sure that passwords, keys, sensitive information does not end up in memory outside your control. So on allocation, it locks memory pages so that if your application is swapped out, the passwords are not in a swap file. On deallocation, it undoes all that and also wipes the data out of memory using appropriate APIs because, as you should know, memset is not enough in most cases. Now, this may be debated whether this is a useful security measure, but it is a pervasive pattern that appears over and over. So let's demonstrate how we use such an allocator. So imagine we have a standard string that holds some sensitive data, and it lives in some scope. In that scope, we talk to the user, maybe compare the passwords. Let's pretend it did not come from a static string literal. So at the end of the scope, the string goes away, the password is destroyed, right? Or not exactly. If we were able to get access to the heap and we looked at it, we might find that exact password still in the heap. In this case, glibc helpfully wiped out the first 8 bytes, but still we have most of that password right there. So what do we do if we want to get rid of it properly? We just change our string to something, in this particular case, Bitcoin support library calls secure string. Nothing else need to do to code, and the password is gone from the heap. So what is that secure string? It is simply a basic string whose allocated type was replaced by secure allocator. This is a case of the most traditional use of allocator, where it's a template parameter that has no special state, has no special rules, just as simple as it gets. And I'm not going to go into implementation details of any of these allocators, because I'm looking at this from the point of view of the user, right? How do we use allocators in code? If you want to talk about implementation, there are plenty of talks at this very conference. This, by the way, I think is an example of where the fact that allocator, in fact, the type of a container is useful, because type system is going to prevent or make it harder for us to move secure data from secure string to an insecure one. Right, now for something that I actually had to do at some point. Imagine you have a system which has a bunch of producers, consumers, aggregators, all sorts of actors that are processing events. And we need to have a long uptime on a perhaps limited memory system. In my case, the uptime requirement was 1 year. It was about 1 reboot per year. And I had a burst rate of maybe 1 million events per second, and we had dynamically reconfigurable system, because once again, we cannot reboot, right? So we had containers that had queues holding shared pointers to events. In this case, I'm gonna build a little demo which shows how it could have possibly worked. So we had, imagine I have a vector of data in my event, and my producers create shared pointers to those, put them on a queue, which is simply a list of shared pointers, right? And consumer presumably takes it off the queue, maybe modifies it, and drops it. So, can anyone see what would the problem if you run this for a year, right? The problem is memory fragmentation. I ran this little demo last week, and just with 50,000 events, I ended up with a system break of 1.6 gigabytes at the end of the run. And double the events, double the system break. Those numbers come from malinfo system called Linux. So this was just unmodified, usual plain Linux user. Of course, we could fix that by maybe using a different malloc, but the traditional and successful approach to dealing with memory fragmentation has always been to use pool allocators, which are now, thankfully, part of standard C++. So how do you use a pool allocator? How do you plug a pool allocator into your program in C++? We need to create a pool object, which has to have a scope larger than the scope of all containers. C++ now has a whole set of different pool types. I'm going to pick this one, since I'm accessing from multiple threads. I have to replace my std vector with std_pmr vector and provide a constructor argument, which tells you which pool to use. This is an example of a stateful allocator, an allocator that takes a constructor argument. And so every standard container has constructors that take allocator arguments. If you have a constructor for vector that takes a size, that is a constructor that takes a size and an allocator. If you have a constructor for vector that takes a pair of iterators, you have another one that takes a pair of iterators and an allocator. And this applies to both PMR allocators and the old allocators that are part of the type. So all you have to do is provide it as a constructor argument, pick the right container type, and that's it. Except for make shared, I had to spell out what goes on behind the scenes a little bit. But if you're working with standard containers, that's very easy to plug in a pool allocator now. When I had to do it, I had to write my own. But as I said, that's not what we want to talk about. So now my system break doesn't grow when number of events grows, and it stays in a much reasonable size. The effects of using pool allocators are pretty multidimensional. There are many different measures by which you can see the effects on performance, and if you want to learn all about that, visit tomorrow's talk by John Lakers called Local Arena Memory Allocators. His numbers are much more reliable than my one-off demo that I just ran. Well, speaking of those dimensions of performance, though, one thing that should be obvious is that we have a single synchronized memory pool accessed from multiple threads. So obviously there should be contention, and this will not scale if I increase the number of threads. Solution to that is another popular pool allocator provided by Intel threading building blocks. This allocator is a size segregated pool allocator, meaning each allocation size goes in its own pool, and it's also thread specific, so each thread has its own set of pools. And there's ideally no contention. Many people use this without knowing it exists because all the TBB containers use one of their own allocators by default rather than standard allocators. But you can also plug it into your own containers very easily. Once again, it doesn't take any special arguments. It goes into your template argument list just as a straightforward replacement for std allocator. So in my case, if I go and replace my vector int with vector int, comma, scalable allocator, and I replace my list, and I replace my make shared with allocate shared, then even though this demo wasn't really built to demonstrate concurrency, it was built to demonstrate fragmentation. Still concurrency effects are quite visible here with TBB allocator. I don't see any change in time it takes to transmit this large number of events, whereas the synchronized pool allocator encounters increasing contention. Notice the vertical scale here is logarithmic, right? Number of seconds, so it took to run. So those were a couple of pool allocators you can use today just right away, except C++ 17 pool allocators. I don't think they've been implemented yet by any of the vendors, so I had to actually use the boost implementation of that and cheat a little. But hopefully they will be available as soon as we have full C++ 17 support. So now for something a bit more fancy, literally. Imagine you have to process a lot of data as fast as possible using thread unsafe code. That's something I had to do once, and the solution we came to was to use shared memory. We put all our data in a large shared memory container, created multiple processes, each of which was manipulating elements in that container concurrently with other processes, so that within each process you have only one copy of that thread unsafe library. And the contents of the shared memory had to be a fairly complicated data structure, which in our case was a map holding strings, vectors, lists, other maps. It was a really non-trivial C++ container. So, but for the sake of the demo, let's talk about vector. What happens if you put a vector in shared memory? In this case, I'm going to use Boost API, which is pretty straightforward. You got a shared memory segment. You can call .construct.net. It takes the type to construct and the constructor arguments to forward. And it just places that object in the shared memory. If I go ahead and do that, and I run another process attached to the same segment, pull out the same object, I'm getting a seg fault when I try to access its elements. So why does that happen? So let's look at what is actually in the vector. The vector is a data structure with 4 elements. 4 data members, right? It has the data pointer, the size, the capacity, and the allocator. The data pointer points to the array of elements which exists somewhere where the allocator told it to exist. In this case, in process number 1, I have the shared memory segment in which I placed the object, but the data pointer is still pointing at my heap because it used the default allocator, which was the secret template parameter of any standard container, right? Now, my second process I attached to the same segment. I saw the vector, started iterating, and I got a seg fault. So to fix that, obviously you need to get an allocator that will point your data vector back into the same shared memory segment as where you are placing your own vector. Now, writing that was really non-trivial, but Boost has a ready-made allocator that does just that. In fact, a whole bunch of allocators do just that. So to use that, it's another case of an allocator that becomes part of your type, so you just supply it to the container as a template argument. But it's a stateful allocator, so it has to use one of those constructors that every container has that take an extra allocator argument. So in my case, I'm going to use the constructor which takes an iterator pair, and I also have to give it an instance of an allocator, or an constructor or an argument is convertible to an allocator type. And now the vector is constructed in that segment, and its data are also in the same segment, and my other process attaches to that, reads it just fine. right? And but as I said, I had a nested container, right? I had a map holding other things. So if we try to do that with, if we try to just take a regular vector of vectors for a demo, and if we use a standard vector of int as a row type, we're going to have a segfault for the exact same reason as before, because even though my outer container uses an allocator that places the rows in that same shared memory segment, that inner vector has no idea that it's going into shared memory segment. It's using the default allocator and it's still putting its data on my heap. So another process, I run my attach to that same vector of vectors, start iterating, and I get my segfault, just as before. Now, if I were to replace that vector of int up there in the row type with vector of int comma allocator for shared memory, it wouldn't even compile because that allocator requires an argument, and there is no way for me to pass that constructor argument down to the row type. The solution for that, Boost actually has its own solution which predates C++ 11, but as of C++ 11, not 17, but 11, we have scoped allocator adapter. I really wish it were available when I had to use this, but scoped allocator adapter does exactly what I want to do here. It takes the constructor argument I pass to the outer container, and then forwards the constructor argument to the nested containers recursively forever. So if I have a vector of vectors, of vectors, of maps, of strings, all of them will be constructed with the same constructor argument that I passed to the outer container. In this demo, I'm placing the vector of vectors in shared memory. I'm giving it my constructor argument that specifies the segment to use, and now I can do whatever I want with the data structure. I can create new rows by those calls, and I will use the same segment. In another process, I can attach it, specify the same allocator, and use it, and I will see all my elements just fine. Scoped allocator adapter is really intimidating if you look at the spec. So don't look at the spec, just use it. It's not that hard. So even though I said I'm not going to be talking about implementations, there is one implementation detail that's actually worth noting. When you attach to a shared memory segment from different processes, that segment appears in a different address in each process memory space, which means the vector's data pointer cannot be an address. It cannot point to your process memory. It has to be a relative offset from something that exists in that same memory, in that same shared memory segment. And in case of Boost, it's actually called offset pointer. This is an example where an allocator has to change what it means to point to an object. This facility was called fancy pointers, like that fancy German wirehead pointer in the corner, or synthetic pointers, as Bob Stiebel likes to call them. And if you want to learn more about those, don't miss that presentation from C++ Now, which talks about how well synthetic pointers are supported by different libraries and what you can do with them. Shared memory is the typical poster child of shared pointers these days, but it's not only one. It's not only case when you have special memory needs and special meaning to what it means to point to something. There's also something that's used in a GPU program, something called pin memory. Pin memory is memory that exists in a specific address and it's used to communicate to a GPU device. It's visible from the host memory. It's also visible from the GPU. You can use direct memory access to communicate. And something you get in CUDA with CUDA host alloc, and you can get it in OpenCL with CL create buffer with appropriate flags. And of course, if you want to put a container in that memory, you got to use an allocator, right? Pretty much every GPU library has something like that. Frost has pin allocator. TensorFlow has an allocator, but that is not exactly STL compatible. And Boost Compute has an allocator, which is also called pin allocator, just like in Frost. With one difference that Boost uses a fancy pointer, which holds a reference to a device buffer and an index, because This library is built to actually operate with data that lives on a GPU. And that's one case where I had to use non-standard vector. The reason being, standard library is designed with fancy pointers that have a mapping to host memory. Because when you call a period of square brackets on your vector, you're going to get a real reference, not a fancy synthetic reference. You should be able to access that directly. So this pointer is a bit too fancy for that. But if you use Frost, it has the same allocator, which uses regular plain ordinary T star as the data pointer. Now, all right. There are many more ready available allocators out there. These are just the first few search results in Debian core search. I think I was on page 3 out of 45. And I could be talking about them for all day. But the main point I want to make is that you don't have to write allocators yourself. You can, but you don't have to. The whole reason allocators being what they are is that they are reusable packaged library components. The components that quite possibly have been written, and if they haven't, they should be written in a way that other people can benefit. And if you do want to write them yourself, there are plenty of talks about doing just that at this particular conference. So I think we have time for a few questions, if you have any.
Should I use the microphone or no? You can just ask it. Okay. So, like one side of the coin of using allocators is plugging in an already written allocator into an already written allocator aware container. But if you write your own type that wants to be a user of the allocator, like looked into this a bit before, and it's also like extremely onerous. Like allocators have all these obscure traits that you have to check very carefully. Copy and move. Do you have any suggestions with that? Is there any library that that makes this a little bit easier that you would recommend?
So the question was that writing allocator-aware types is onerous because of all the allocator traits that you have to look at and the allocator propagation semantics you have to take care of, and whether there is an existing library that simplifies that. So no, I don't think there is one. In fact, the talk by Alexander Meredith just before this one was about one of the ideas of how it could be made simpler in future. And I believe a talk by Pablo Halpern will be about the details of propagation traits and all those related things. But yeah, the status quo is that writing your own allocator-aware container is not trivial, especially if you want to be able to use that allocator into something that propagated down the chain into something you hold, right? Anything else?
I saw an allocator with the name random throws. Are those to be used a lot in like testing, just generating random like memory problems when you allocate?
So the question was whether there are allocators that generate random memory problems. I imagine yes. I've seen allocators and I've used allocators that are used for instrumenting and debugging and analyzing memory problems, and allocators used for unit tests. I haven't used the fuzzing allocator. This will be a nice segue to the next talk, which will be right after this one. But yeah, it would be interesting if there is someone like that available right now. I haven't encountered yet.
For the boost compute allocator that returns its own fancy point plus other,
right?
And then you have to use boost compute vector with that. What do you get when you dereference one of those fancy pointers?
Okay, the question. Okay, yeah. The question was what happens if you dereference a fancy pointer that you get from Boost Compute, device pointer. What you get from that is a special iterator that they provide, a device iterator, which is essentially a fancy accessor to the data. But yeah, it's not directly pluggable into standard containers because it's not a contiguous iterator. You cannot just take its address and do pointer arithmetic on that. Yeah.
So I couldn't understand the chart very well. There was 1000x. So what does it mean? Like, can you explain the graph from the chart?
So the question was what the 1000x was about in my slide on memory fragmentation improvement. So when I ran this demo using standard allocator on Linux, I got my system break of 8 gigabytes. So when you use malloc on Linux, you have your allocation goes either into system break, which is the first contiguous heap space, or goes into mmap areas, which are all over the heap. And system break usually just grows, it doesn't shrink. And if you deallocate something, you don't actually incur a system call. You just leave a hole in your system break, and if you're lucky, it's going to be filled back in if the malloc understands, if it is able to find it next time it allocates something in the same size. I had many mismatched size allocation here, and those mismatches caused it to build up a very fragmented heap. So I had a massive system break of 3 gigabytes. Whereas when I ran through the pool allocator, I ended up with not growing that system break at all. At the end of the run, I had only 3 megabytes. Now, this is a one-off demo, so your mileage may vary. But it represents something that we actually saw in production, dealing with something that ran for a year at a time. All right, anything else? Going once, going twice. All right, thank you for listening to my talk.